Welcome back, everyone. In my last Calculus 3 video, I went over the derivatives of vector functions. So, in this video, I'm going to go over the integrals of vector functions. Just like taking the derivatives of vector functions, when you take the integral of a vector function, you are taking the integral of each of its components functions, f of t, g of t, and h of t. And as you know, those represent the functions for each of the coordinates x, y, and z. Taking the indefinite integral of vector function lowercase r of t gets you its antiderivative, capital R of t, plus constant vector c. C contains within its components the arbitrary constants from integrating each of the components' functions. We can label them c1, c2, and c3. The same concept applies when taking the definite integral of a vector function from t equals a to t equals b, given that f, g, and h are all integrable on a to b. This section on integrals of vector functions is very straightforward. The new concepts in this section in the scope of Calculus 3 are that you're taking what you know about integration and you're applying them to vector functions, and also the applications of position, velocity, and acceleration. But aside from that, it's mainly just integration review. So I'm going to be doing 4 examples in this video: an indefinite integral, a definite integral, a problem with an initial condition, and finding r of t from a given acceleration vector a of t. Alright, so for example 1, we want to integrate r of t dt. And yes, this process is as simple as it seems. So we start with the first components function, 3t squared, integral of 3t squared dt. Using the power rule, that's going to be t to the third power plus arbitrary constant, which is going to be c1. Next, we have the integral of sine of t dt. That's going to be negative cosine of t plus c2. And then the integral of e to the t dt is just e to the t. And then we have plus c3. So we could say the integral of r of t dt equals t to the third power plus c1, comma, negative cosine of t plus c2, comma, e to the t plus c3. You can also write the constants as its own vector, so you could also just write it out like this. For example 2, we're given r of t, and we want to evaluate the integral from 0 to 2 of r of t with respect to t. So first, I'm just going to write out the integral within each of the components. We have the integral of t to the third power. That's going to equal 1/4 times t to the fourth. And then we want to evaluate the integral from 0 to 2. Next, the integral of cosine of t is sine of t. We evaluate the integral over the same interval. And then for the integral of t times e to the t, we can use integration by parts. So if you recall, that's the formula for integration by parts. We want to set the variable u to the part of the function that is harder to integrate. The acronym ILATE helps prioritize what u should equal. And this stands for inverse trig, logarithmic, algebraic, trigonometric, and exponentials. T is algebraic and e to the t is exponential. So we want to make u equal to t. And if you take the derivative of that, you'll get 1 dt. That's what du is equal to. So we set u equal to t. So dv is e to the t dt. And to get v, we have to take the integral of that. The integral of e to the t is e to the t. And now we can form this piece. So first we have u times v, that is t times e to the t, minus the integral of v, which is e to the t, du, which is 1 dt. And then this part is equal to e to the t plus c, the arbitrary constant. However, in our example, we're evaluating a definite integral, so we won't need the plus c. So evaluating at the bounds, we'll have 1/4 times 2 to the 4th power minus 1/4 times 0 to the 4th power. And then we have sine of 2 minus sine of 0. And then 2 times e to the 2nd power minus e to the 2nd power. And then the quantity of that minus 0 times e to the 0 minus e to the 0. So 2 to the 4th power becomes a 16. Divide that by 4, we'll get a 4 minus a 0, comma, sine of 2 minus sine of 0, which is just 0. And then e to the 2nd power minus e to the 2nd power. That just gives us 1 e to the 2nd power. And then in the second parentheses, we'll have 0 minus, and then e to the 0 is 1. So this becomes e to the 2nd power plus 1. For example 3, we're given r prime of t, and we want to find r of t if r of 0 equals the vector 2, 1, 0. This part right here is the initial condition. We're going to use that after we find the integral. We know that taking the derivative of r of t gets us r prime of t. So if we start with r prime of t, integrating r prime of t gives us r of t plus the constant vector. So we could say r of t equals the integral of r prime of t dt. So first we have the integral of t to the 2nd power plus e to the t. That's going to be 1/3 times t to the 3rd power plus e to the t plus arbitrary constant c1. The integral of t times cosine of t, we can use integration by parts. T is algebraic and cosine of t is trigonometric, so we'll set u equal to t, and then dv would equal cosine of t dt. So that's the integral of u times dv, that part. Taking the derivative of t, we can find du, which is 1 dt, and then v is the integral of cosine of t, which is sine of t. So now we can write out this part. U times v is t times sine of t. And then we have minus the integral of v du, which is sine of t dt. And then the integral of sine of t with respect to t is negative cosine of t. And then we have an arbitrary constant. So going back up here, we can write t times sine of t plus cosine of t plus c2. And then to get the integral of sine squared of t, we can use power reduction. We can rewrite sine squared of t as 1 minus cosine of 2t all over 2. When rewriting the integral, I split the denominator over the difference. So the integral of 1/2 with respect to t is 1/2 t, then minus. Now we need to take the integral of 1/2 times cosine of 2t. The integral of cosine is sine, and we'll keep the argument the same. If we were to take the derivative of sine of 2t, we'll have the cosine of 2t, but with the chain rule, we also have to multiply the derivative of 2t, which is 2. The constant up here is 1/2, so something times 2 has to give us 1/2, and that something is 1/4. So to finish out the integral, we'll have a plus c. So it's going to be 1/2 t minus 1/4 times the sine of 2t plus c3. So now we have r of t with constant c1, c2, and c3, and this is the part when we can apply the initial condition. So we have r of 0, so we'll plug in a 0 for t, and then we can set this equal to 2, 1, 0, and now we can solve for c1, c2, and c3. And we do this by setting the components equal to each other. So for the x component, we have 1 plus c1, and we set that equal to 2. And then we set 1 plus c2 equal to 1. And then c3 just equals 0. So now we can take these values, and we'll put it back into the r of t function. So r of t equals 1/3 times t to the 3rd power plus e to the t plus 1, comma, t times sine of t plus cosine of t, comma, 1/2 times t minus 1/4 times sine of 2t. Example 4. A particle moves through space so that its position at time t is given by a vector function r of t. The particle's acceleration vector is a of t equals 6t comma cosine t, comma -2 sine of 2t. Initially, at t equals 0, the particle is at 1, 0, -1, and its velocity vector is v of 0 equals 1, 0, 0. So remember, to get velocity vector v of t, we take the first derivative of r of t. And to get the acceleration vector a of t, we take the derivative of v of t or the second derivative of r of t. So if we want to go from a of t to v of t and v of t back to r of t, we would need to integrate. So v of t equals the integral of a of t with respect to t. So we'll get 3t squared plus c1 sine of t plus c2 and cosine of 2t. If you take the derivative of cosine of 2t, we'll have the negative sine of 2t and then multiply by the derivative of 2t, which is 2. And then we have plus c3. And then we can find c1, c2, and c3 if we apply the initial condition. V of 0 equals 1, 0, 0. So this is what we get when we plug in 0 for t for v of t. And this equals the vector 1, 0, 0. So c1 equals 1, c2 equals 0, and 1 plus c3 equals 0. So c3 equals -1. Let's plug these back into the velocity function. So to get r of t, we'll take the integral of v of t. So the integral of 3t squared plus 1 is t to the third power plus 1t. So we can call these next constants c4, c5, and c6 so we don't get confused. And then the integral of sine of t is negative cosine of t plus c5. And then when taking the integral of cosine of 2t, the integral of cosine is sine. We keep the argument the same. And then the derivative of the argument is 2. So there's a coefficient of 1 in front of the cosine here. And then the coefficient here multiplied by 2 has to give us 1. So we would have 1/2 right here. So the integral of cosine of 2t minus 1 is 1/2 times the sine of 2t minus 1t plus c6. And then our initial condition for r, initially at time t equals 0, the particle is at the point 1, 0, -1. So the vector r of 0 equals 1, 0, -1. That's our initial condition for r. So plugging in a 0 for t for r of t, this is what we get. And we set this equal to the vector 1, 0, -1. c4 equals 1. -1 plus c5 equals 0. So c5 equals 1. And c6 equals -1. And we'll plug this back into the r of t function. So in the end, we should get r of t equals t to the third power plus t plus 1, comma, negative cosine of t plus 1, comma, 1/2 times sine of 2t minus t minus 1. And let me show you what the curve of r of t looks like on a graph. Alright, so the blue line is the curve r of t, and then green is a point on that curve, and then that green arrow is the r of t vector. Right now t equals 0, so r of 0 is 1, 0, -1. What you see in red is the velocity vector. It is going to be tangent to the curve at a given point, and right now it is v of 0 specifically. And then purple is the acceleration vector. If we plug in 0 into t for a of t, we'll have a of 0 equals 0, 1, 0. So here's the vectors and the point at t equals 0. And now I'll move the point in the direction of increasing t values so you can see how the vectors change.